let's consider a different application of L'Hopital's rule, where we're looking at this function x to the 2x. That's defined for all x greater than 0, but the problem when x approaches 0 from the right is that this is also considered an indeterminate form, 0 to the 0. Part of this is because we think of 0 being raised to any power as being 0, but we also think of any number being raised to the exponent 0 as being equal to 1. So the question is, should 0 to the 0 be 0 or should it be 1? We can't really apply either rule. It turns out that we can think about this problem using L'Hopital's rule. So let's start and let's define a new function, h of x. So h of x is going to be natural log of g of x of this function. So we have h of x equals natural log of x to the 2x. Now, because of rules of logarithms that say that if you have natural log of a to the b, you can bring that b down in front. This is not taking a derivative, this is just a rule of logarithms. We can do the same thing here, that h of x is equal to 2x times natural log of x. Okay, and this will allow us to analyze this problem in more detail. So 2x log x, if we think as x approaches 0, again, we're going to have this problem that this is approaching 0, but this is approaching negative infinity. So it's this indeterminate form of 0, so 2 times 0 times negative infinity, and that's indeterminate. So what we'll do instead is we'll try to convert this into an indeterminate form where L'Hopital's rule applies. In particular, we'll take this x and move it into the denominator. So in the denominator, we can write 1 over x. So the reason that this is equivalent is because we said h of x is 2x log x. And now what we can do is we can think of that x as being 1 over x. Okay, so that becomes 2 times 1 over x times log x. And if we put the 2 and the log x in the numerator, we get 2 log x over 1 over x. Now, what's nice about this is the 2 log x, so as x goes to infinity, not go to infinity, as x goes to 0 from the right, 2 log x goes to negative infinity, and 1 over x goes to infinity. So now we have this form of infinity over infinity, and L'Hopital's rule will apply. Okay, so the limit as x approaches 0 from the right of h of x, which is 2 log x over 1 over x, because we've already determined that it applies, that it looks like infinity over infinity, we'll keep the limit. We haven't taken the limit yet. We'll take the derivative of the numerator. We'll take the derivative of the denominator. Now, we can see that this is going to simplify quite a bit. So we have 2 over x times this negative x squared, right? Because this part, when we flip it, we get negative x squared over 1. Now we can see one of these x terms is canceling. So you get the limit as x approaches 0 from the right of 2 times negative x, so negative 2x. And now if we plug in 0, we can see that this limit is equal to 0. But we are not done yet, because remember, this is the limit of h of x. Now g of x, h of x was defined to be, if we go back up, the natural log of g of x. So h of x is the natural log of g of x, which means that g of x is equal to e to the h of x. Okay, so if we're curious about the limit as x approaches 0 from the right of g of x, this is equal to the limit as x approaches 0 from the right of e to the hx. And because e to the x is a really nice function, it's continuous everywhere, we can bring this limit inside. This is a rule of limits that we have not used for quite a while, but it's a rule that says we can take this limit inside. And then now we have already computed this limit up here. We said that that limit is 0. So we get e to the 0 from the right, which is going to be 1. Okay, so this says that this function, let me write it up here, the limit as x approaches 0 from the right of x to the 2x, which had this indeterminate form 0 over 0, but we were able to use L'Hopital's rule and analyze it more, that this is actually equal to 1.